Hi everyone, this is V.Thiagarajan, a retired deputy chief engineer from Indian Railways. So in this video, we are going to discuss something about the curved track connections and crossovers, along with the numerical examples. So earlier, I have uploaded some videos for layout designs, part 1, 2, 3 and all, and that is for for various type of connections. But in this video, particularly, we are going to see something about the curved track connections and crossovers. So along with the numerical examples. Okay, it is a part 4 video. Okay, connection between two curved parallel tracks. Now we are coming to the earlier we have seen all parallel tracks, non-parallel track, only straight tracks we have seen. Now this is something about the curved tracks connections. But it is little complicated because involving a lot of formulas. But earlier, case and all we have been seeing adopting Sunderland method, but here we don't adopt Sunderland method. And okay, keep the two lines, gauge lines as it is, and we are finding out the connecting of radius how much and distance from the theoretical NOSA crossing. We are keeping all distances references. Okay. So this and all we are doing it, but it is a little complicated, and we will see. But here I am not going to completely see all formulae how it is resolved trigonometrically and all, and just giving some brief. I will just take the important formula. With the important formula, we can straight away go for the required parameters, finding out what fixing geometry on the field as well as curved connection is concerned. Okay. So here, so this much derivation we have to make, trigonometrically, we have to solve for, this theta and the kinetic radius and the x distance. So here you see, actually, in this case, we are taking the gauge line as it is, complete track as it is we are drawing, and here we are finding out the connecting radius of connecting how much we can fit, here we are finding out. Then for fixing the distance, the x distance is here, not here, it is not Sunderland method, here with reference to only crossing, with reference to the crossing of the points on crossing to the point where the tangent, the curve ends, the tangent point. Okay, that is along the curvature, outer rail of the inner curve, main line curve. Okay, that distance we are marking, then we are fixing it. So further, we need to know this distance, the theoretical loss of crossing to the tangent point. We must calculate x distance. Then radius of the connecting curve, of course. Then we have to find out for that, we have to find out the theta angle we have to find out. So this three formula is essential here. For this type of connection, we have to find out the theta first using this relation. Then we have to find out the radius of connecting curve using this one, and at last the x distance. Okay. Here the k distance and all here, that we have seen Sunderland method. Sunderland method, B portion we have m plus k. That k distance is standard distance we are taking from the table. That's all here. Okay. So with this we have to solve for the required parameters as with this type of connection is concerned. Okay. So we will see an example here. This is a curved parallel track. Center to center of track is 4.725. Connection being made on outside of the main line curve. Here it is a main line curve. Outside connection, the loop line or siding connection is outside. Okay, without a straight after the heel of crossing by using one end of crossing. Here is one end of crossing. So in this case, how to do the connection? That means we have to find out the radius of connecting, how much we have to find out, and when we are starting the curvature from heel of crossing, where should the end, the tangent point. That further we need to know the x distance from theoretical nose of crossing to the tangent point. Okay, we have to find out. and for all calculation we need to know the theta angle. So as already seen the previous slide, so theta we can find out using this relation, theta equal to, so this relation formula we can use it. So further we know distance, we know 4.75 g, we know, okay, this 1.616, everything in meter, and k we can get from this one. So even k, actually k is what, so we have discussed already. Now we have seen the central representation of points of crossing. Here this is our point of intersection, that means central of the main line, turnout line, intersecting point is point of intersection. From SRJ to the point of intersection is called A, and point of intersection to the heel of crossing is B on both sides. But B is divided into two parts. There is M and K. M means point of intersection to nose of crossing, that is nose of crossing, and K is equal to TNC to heel of crossing. Like this side also. So this K only, as far as this type of connections we need this K. The K is, that means theoretic nose of crossing to the heel of crossing distance you must know. So that is also available in standard dimension table. So from here they are taken here actually. So I already know this is the table we given, but in the example they are given 3 point something, but we have to take 5.516. But latest we are using CMS crossing with PS slipper. PS slipper K is modified, so B is modified, K is modified. So because of that, okay, this we have to follow. Anyway, for example sake, this is a old type of crossing, other than PS slipper. That is why they have taken 3.123. Okay, we have it. So this is actually the K. K is the TNC to the heel of crossing. The standard dimension available here. Then angle of crossing we know. Again RM, main curve radius also is given. How much? So 450 they given. Okay, 450 we can take. Again D distance we know, G everything know. So once we know everything we can find out the theta here. So once we got the theta, we can substitute in this other formula for knowing the radius of the connecting curve. So RC equal to this big formula we are using it. Here also theta we have found substituting here. RM we know, K we know, angle we know, everything we know. G also we know, K. So all known values we are substituting it, we are getting the radius of the connecting curve. Then subsequently we are finding out the x distance, that means this here TNC to the tangent point along the main curve, inside curve, outer rail. We have to measure that distance. Outer measure this here tangentially and vertical distance marking that will determine the tangent point of the connecting curve. Okay, this is also outer radius. So here for x equal to K plus RM. Okay, RM theta actually pi by 180 for converting into radian into degrees. So at last we are getting 3.123 plus this value we are getting 48.877 meter. Okay, that means this length equal to once it's r theta. Once theta, the arc length equal to how much? So r into theta in radians. And theta we are converting into pi by 180 into, when we are doing it we will make it in degrees. So we'll get the x distance, that's all. Up to this point. Then plus we are adding the k distance, that's all, 3.12. This is the concept. Okay. So that's this is a procedure. Okay, we have to follow that for finding out the x distance. Okay, this is something about it. This has been measured along the outer rail and in inner track. That is why straight away taken simply r theta. So as far as this case is concerned, actual radius is outer rail radius, but now whatever distance we are measuring along the inner rail of the outer rail track, that is why total r minus g they are putting. So total r minus g. Only the difference we make here. Okay. For converting into degree, we are adding pi by 180. Okay. This is something about it. With this, we can proceed. Go ahead. Okay. So as far as this type of connection is concerned, is also curved track. But here, it is not a similar flexure. The earlier two cases, we have seen a similar flexure because both the main line and the siding line was, both are fluxing in the same direction. But here, that siding line is taking off away from the main line. So in opposite direction, it's a contra-flexure. I used to say it is a contra-flexure type. And here, how to proceed here? So here also trigonometrically, so they solved some equation, and finally they are getting the x distance. That means theoretical nodes are crossing to the point, on a main line, and from there, we are keeping an angle equal to delta. That line, is coming line. This also delta is known. Coming line is known, and radius also we are fitting. So RM already we know the main radius, and connecting radius also we are only feeding. We are giving the input. I mean this delta also we are giving the input, because when the line is coming, so what is the angle? This angle makes with the main line tangentially. So that delta also we are measuring. Okay. So with that we are resolving. Here R1 equal to RC plus K tan Phi2. So R1 they are first they find it, because in this there are two triangles, that O1 and A and N. Another triangle O2 A and N. There two triangles are there. And further, if you take your RC, the RC is up to the curve. After that, some distance is there. That distance means this RG means come up to this point, then plus the AG distance. This is the enlarged, drawing of this portion, the crossing portion. This is your nose of crossing. This is your heel of crossing. This nose of crossing. Other side is heel of crossing. So the angle is total IF f by 2, and it's a bisector. So this line is okay. This line is they made this line. Okay, this line. So this line is actually this is here. Okay. So R1 is up to this point, O1 to A. That is why they taken RC plus that's G equal to K tan F by 2. Okay. Like that R2 equal to RM, okay, up to H plus K tan F by 2. So that's what here. Okay. So the R1, R2 we need for resolving this equation. From there we are trying to find out this phi angle. Okay, the phi angle, that is cos phi equal to this equation they are forming. Then for finding out the theta angle, they are forming this equation. This theta angle, they are forming this equation. Okay. So everything we know, RC, K tan F by 2, the crossing angle, R1, R2 also we have found out. So once we know, we are able to get the theta angle. Like that, using this relation, we are able to get the phi angle. The phi angle equal to cos inverse of this thing. Like the theta is equal to sine inverse of this thing. Once we know, we can come to the x part. That means distance from theoretical nodes of crossing to the point, okay, where the site branch line, the extension meets with the main in curvature. Okay, so that point, up to that point, okay, this is x, and this x is we are finding out using this relation. So R1 squared plus R2 squared root of plus 2 R1 R2 cos of this sine here phi we are finding out using the relation, and minus Rm sine delta also already we are measuring. Okay, this is input actually. Okay, input data. Use the relation, we are able to get the x distance. And coming to y means what? This distance we are finding out. Okay, from the point now between the siding track and the mainline track. The distance is y. Okay, we are fixing the offset, giving the angle equal to delta. So that is equal to k plus r psi. K plus r psi. R psi means what? This is your psi. This is your psi. So this angle there, this distance we are arc length we are finding out. R psi equal to this arc length, this distance, and this is in radians. Okay, psi in radians. If you want to convert it into degree, so r psi into pi by 180. Okay, so this distance plus k we are adding. K means what? Theoretical modes of crossing to heel of crossing, that k length. This is standard dimension value. So you are adding that, you are getting. But what is psi value? Psi is equal to delta minus, okay, phi plus theta. So you know phi plus theta. Here now we are finding out theta, theta equal to sine inverse of this much. So from this relation you are able to get this psi value we are substituting here. So this is the way we are calculating the required parameters, and with that help of these parameters we are able to fix the geometry on the field x, then y distance. Okay, that's all. This is something about the contraflexure. Then we will see an example for the contraflexure type of connection. Okay. A curved track of 450 meter radius is required to be connected to a straight track intersecting the outer rail of the curve at an angle of 30 degree. The connection is to be laid by means of 60 kg PSE. One unit of turnout and a connecting curve of 300 meter radius. Okay, here they are given what the radius of the main curve is given, the radius of the connecting curve is given, that is 300 meters. This is 450 meters, and then the line is coming here. This is siding line. This is your main line. The line, the extension is just intersecting the main curve. At the point of intersection, we make tangentially the angle. What it is making is 30 degree. So 30 degree. That's what it is given. The points on crossing used here 60 kg PSE 1 in 8.5. So we have to perform connection. So to be done, and for that what to do? We have to find out the x distance and the y distance. Connecting curve, it is we are only providing connecting curve for this curvature. At what distance, we have to fix this y and x. Once we know the x, can mark the TNC position. Accordingly, you can insert the points and crossing. This is the procedure, and for that we have to calculate the x and y distance. Simply we can take all formulae whatever we have discussed in the previous slides. Okay, we have formula. You have to find out the R1, R2. This R1 is what this two triangle. We have two triangles. R1 is this one. That means RC plus this GA. Okay, like that. That means R2 means there is RM plus HE. So through this equation we are getting R1, R2. Then cos phi we are calculating using this relation. Okay, once we know the phi, substituting all values here, and phi can get it. And sin theta, another formula we got. Sin theta we have to use here. This formula we have to use. So from this formula we are able to get the phi value. This formula we are able to get the theta. Once we know the phi and theta, you can find out the psi value. Psi means this angle. This is your theta. This is your phi. We want to know our psi angle. Psi equal to delta. Delta means whatever angle it makes. Here 30 degree. So 30 degree here minus of phi plus theta. So this is using this relation we are able to get the psi value. So once we know the psi, Okay, we can substitute here x formula. To get the x distance, x equal to k plus rm psi 190. Rm psi. K plus rm psi. This is your rm. So rm psi will be equal to this distance. Adding this k distance, we are able to get the x distance. But psi is in radian. If we want to convert to degree, we are multiplying by pi by 180. Okay. So through this, we are able to get 39.223 meters. This is our x distance. Then y distance, this distance we have to find out. Okay. So what we are doing, we are making the extension here, intersecting the point. Okay. From here, we are making x distance, and accordingly, in order to get TNC here, and we are inserting the points in here. And after that, this point we are marking. So this will be tangent point, this y distance. The y equal to this formula we are using it. Using this formula, we are able to get 68.113 meter y distance. From here, we are marking 113. That will locate your tangent by the curve. So once you fix this position, once you know this tangent point, we can introduce the connecting curve, so that we will be able to get a radius of connecting curve equal to 300 meters. Okay, this is a procedure we have to follow. Okay, as far as contrafracture is concerned. Okay, then coming to crossover between two curved parallel tracks. Here, just like a straight parallel track, we introduce a crossover. Here we introduce 2 points and crossing, 2 turnouts on both lines, each one. Okay, and we are giving the connection. This connection here will be a curved connection. Okay, so in this case, for fixing the layout, what we want this x distance. That means the distance between the theoretical loss of crossing of the first point to the other point. Okay, we must know. And also radius of the connecting curve also you must find out. Okay. Here being the curved track, the procedure is very lengthy. Here you see we want to solve trigonometrically for the connecting curve. These many lines are there, you see. Okay, and we take rm equal to radius of curved main line, outer rail, and RC equal to radius of connecting curve, outer rail. Okay, so with this we are deriving, and finally our RC formula equal to this one. RC equal to, so this big equation, it is for finding out the RC. Substituting all the values, we are able to get the RC. Here of course RM mainline radius that we know, and D distance between the curved parallel tracks. Okay, that's also known. And G this gauge, broad gauge, 1.676 meter we take. And K, of course, we have the value, standard dimensions AB. The B is split into M and K. That K value is K. So we can take from the table of standard dimensions of each point. Okay, different points and crossings. Okay. Then for finding out theta, it is must, because for finding out our x distance, we know theta we have to find out. So for that, so many lines are there, and ultimately we are finding the theta also here. So but anyway, our x distance equal to this formula. Okay, so these are the equations we are using for finding out the radius of connecting curve and the x distance. With that, we will be able to fix the geometry on the ground as well as crossover in case of curved two parallel tracks is concerned. Okay, we'll see the example also. Here, a 60 kg PSC 1:12 crossover is required to be laid between two curved parallel tracks. Assuming the radius of outer rail of the inner track as 1000 meter and the track center as 5 meters, calculate the various parameters for the layout. Okay, this you have to find out. F is given, crossing angle 1:12 points across we are using. K, of course, this standard dimension of K and the 1:12 turnout. The K value we can take from the table. Okay, so using this formula RC, so ultimately we are finding out the value. Okay, here we know RM, we know D, G, everything is there. Substituting all the values, and finally we are getting, you see, RC equal to here 1069.703. Okay, radius of connecting curve. And for finding out x, we have to solve theta. So theta, we are substituting all these formulae and all, and finally we are finding out the x distance. X is equal to theta, we are finding out, that is 0 degree something, and x equal to, substituting here, see all k, d, k, everything is radius of main curve. Substituting all here, we are able to get the x distance, that is 19.652. Okay, but here you can see, it's very cumbersome. Okay, for calculating our radius of connecting curve, and x distance is a cumbersome process. But already it has been studied. Even the same problem, when we are considering as a straight parallel track and introducing crossover. Okay, when you are calculating the x distance, almost equal. So when you are keeping as curved parallel track, introduce a connecting curve, and when you are keeping a straight parallel track, introduce a crossover, and both the case, the x distance will be almost closed. Only the marginal difference will be there. It's all meager. So that is why, instead of following this cumbersome procedure, we can consider, that is the case, we can consider both tracks are straight, and including the crossover, we can find out the x distance. You can see here, and in case of curved parallel tracks crossover, the x distance is about 19.652. But when you are considering as a straight parallel tracks and introduce a crossover, the x distance is coming around 19.71. Okay, so only the difference is 5.8. So it's only a meager. That is why, so straight away you can use the consider as a straight parallel track and introduce a crossover, and further we can find out the x distance. Here the x distance is little different. It is not different. See, the x distance here is the distance between the theoretical nodes of crossing of one point to another point. But whereas normally when you are finding out our x, what we are doing, x equal to d cutoff. That is center line method. Okay, that is center line method. That means that the x distance is from points of intersection of one point to point of intersection of other point. That means the distance has to be directed. So that distance equal to, this distance equal to g by 2 cot f by 2. Since we have both sides, this side one distance is, that side one distance is. That is why they are deducting g cot f by 2. So once you are deducting, we are getting the x distance, the straight parallel track, that is from the theoretical nodes of crossing of one point to other point. Okay, that's why they have taken. Okay, however, this difference is very much meager. And also for various degree of curve, in case of only 12 points across, we are introducing in crossovers, and they have calculated treating the as a curve, that means curved parallel track, 2D curve this much, 97.513. But in the case of straight parallel track, it is 97.578. Only 65 mm difference is there. Like that for 2 degree, 3 degree, 4 degree, 5 degree, they calculated, for curved parallel track, how much length of overall length we are getting, and in case of straight parallel track, how much overall length we are getting. The difference is 65, 97, 129, 162. Well, the difference is very meager. Okay, that is why we can side away follow the straight parallel track. We can introduce a crossover. We can fix the overall length, SRJ to SRJ, we can fix it. But only thing, radius of connecting curve, we have to find out. And for that also, once you are fixing it, you can extend the straight line. Here, suddenly you can extend, here extend, it will intersect one point. So that will be intersection point. Okay, and we can calculate the or measure the deflection angle as well as the length from the heel of crossing to the intersection point. If you are measuring, that will be your tangent length. And deflection angle also we can measure, the deviation. So once using your tangent length and the deflection angle, you can find out the radius of connecting curve. Okay, for that connecting curve, we can radius of connecting curve, we can set out the curve here. Okay, so that's all about crossover between curved parallel tracks. Okay, this is something about it. So then coming to goods yard, you see here. In case of marshalling yard, you see sorting yard, where there will be so many lines will be there, and goods trains will be dealt here. So there the wagons will be segregated, sorted out, and for that we will be requiring number of lines. Okay, So normally this will be laid in this way, forming one ladder track will be there. There many tracks will be laid parallel. Okay. So this is a type of goods yard we are seeing now. So here in this case, we are having a different type of gathering lines. We have ladder track. So here gathering lines laid at an angle of crossing. That means this is a we want to form a yard with a ladder track. So when we ladder track, we are keeping an angle equal to angle of the crossing. This will be here. That means when we are using one end of crossing here, and the angle of ladder track also equal to one end of angle. That means 60 degree something. That angle will be there. So once we are laying this points and crossing, and our ladder track alignment will be like this, and we can consecutively we can introduce points and crossing and giving the connection for the various lines here. Okay. Duly maintain a distance equal to d. Okay, the minimum distance prescribed. Okay, in a manual. Okay, that is to be done. Here how it is to be done, you can see here. Suppose this is your points and crossing. First we are laying out. Next points and crossing, where you have to lay the other for forming the other line. So here as usual, we have got to find out the distance x. That means our point of intersection of the first point to other point we have to find out. And for that, we know pretty well the equation, the x equal to d cot of this triangle. Okay, this triangle, once d is fixed, suppose we fix some 5 meters something, we are fixing it. 5 meter means what? When you are using 8.5 crossing, means 5 into 8.5 will be your this x distance. Okay, d cot of number into distance will be. So once you fix your point of intersection here, from this point, the same alignment, we can come forward for a distance equal to a. That will locate your SRJ of these points on crossing. Suppose, okay, points on crossing. Suppose exactly is butting with the heel of crossing, you can connect it. If there is any gap, you can introduce a strike between. According to the distance, whether there will be yes or there won't be any straight portion. Okay, if the distance is very close and there won't be any yes. If the distance is somewhat keeping large, and there will be some guardrail, okay, involvement will be there. Okay, like that every point of intersection will be fixed, and we are able to fix the point of SRJ of that point coming forward for a length equal to a of the points across. Okay, so like that x1 equal to here how much d cot of that, x2 next point how much, double the x1, that means 2x1, x3 triple the x1. Okay, like that we are able to fix the point of intersection of the various points for forming the lines. Okay, parallel lines. So this is something about it. If we want to find out the distance between the point of intersection along the ladder track, that my hypotenuse, so we use this relation. That means sine formula we are using it. That means sine theta equal to relating what, opposite side divided by hypotenuse. Opposite side we know d, and hypotenuse, suppose you want to find out, sometime when it is no s means that will be plus d. Otherwise we can find out the LL distance, so that we will be able to know whether any straight length is required or not. So for finding out the LL, this equation will come like this, d by sine of. That means sine of equal to d by LL, and LL equal to d by sine of. So okay, this is the way we are finding out the length between the points of intersection along the ladder track. Okay, these are the formula we are using it. Okay, this is one way of arranging your yard. Okay, ladder track. And here what will happen, since it is so slanting, so this area will be wasted. Okay, and also the line capacity, the road capacity, each road capacity also will be reduced slightly. So in order to avoid this wastage of space, what we are doing, slightly we are keeping the ladder track close to the vertical like this. Okay, in a next type, ladder track at a limiting angle. In this case, since we are slightly bringing the ladder track close to the vertical, this area will be able to utilize. At the same time, the road capacity also will be increased. Okay, so since the angle of ladder track is more than the angle of crossing, so there will be a necessity of introduction of a connecting area here. Okay, tilting it, and you have to introduce a connecting error. So in this case, the Q minimum, how much angle we can provide. For that we are using this relation sine of inverse of d by a plus b plus s. That means suppose this is your ladder tracking. You can take this portion, point of intersection, to other point of intersection. See what is here hypotenuse will be. Hypotenuse will be here a, okay. This is B and A, and in between S. That means A plus B plus S will be your hypotenuse length. And vertical distance we are keeping as D. This D will be equal to this, actually this D. The vertical distance between the point of intersection. Okay, this point to this point. So D. So as usual, now sine rule we are applying. Hypotenuse and opposite we are applying sine rule. That means sine Q equal to opposite side D divided by hypotenuse. Okay, that means hypotenuse means A plus B plus S, and Q equal to sine inverse of D by A plus B plus S. That's what here, okay, made it. So by finding out the Q minimum. And tangent length, of course, here we want to introduce a kinetic law. To find out the tangent length, we are fixing the radius, okay, for a prescribed radius. And here we want to know the deflection angle. So in this triangle, see, this angle will be equal to Q minus F. Okay, that sum of internal angles is equal to external angle. That means this angle will be equal to Q minus F. So T equal to R tan deflection angle Q minus F divided by 2. Okay, this is something about it. Okay, then coming to see different. Suppose we want to, sometime we want to introduce straight portion, sometime we don't want to introduce straight portion. We used to connect directly, the connecting curve, this one will be without any straight, directly will be connecting. So in this case, how to proceed? The case 1 equal to, when S is 0, Sj lies immediately after the curve. Okay, like this. Another case with S, like the two cases are there. First case, suppose we want to find out the D minimum. If you don't want to have any S, okay, S is equal to 0. In this case, the D minimum equal to B plus T sin F sin Q minus F plus T plus A in sin Q. Okay, that means you can take this triangle, first triangle, this triangle, and next triangle, this triangle, and third this triangle. Okay, this triangle, 3 triangles now, so that from here sine rule we can apply. We can find out the D minimum if you don't want to have any S. So T we are finding out using this relation. Yeah, that's what they have made it here. Only this triangle, this is what this vertical distance, how much this vertical distance is equal to this one, hypotenuse B plus T sin F. So coming here T S A will be there. So T plus A and sin Q will be this vertical distance. And here what, this is your B. So here angle is Q minus F. Q minus F. You see Q minus F and B relating it, and we will be able to get the vertical distance. So in adding all, we will be equating the D minimum. So that will be the equation formed like this. Okay. And in case of case 2, and we keep yes, it's a straight portion. Suppose we want to have the D minimum. For example, suppose is D minimum, if it is simply 8 meter, we can't accommodate one more line. Suppose you want to accommodate one more line in between, we can freely keep some 10 meter. So what 10 meter length when you are keeping, so what will be the straight length we have to fix, like that we have to find out here, so that you can keep this line 10 meter interval with the distance, so that one more line we can introduce here. This area also will be utilized. Okay, and for this case will come and we can utilize it. Okay, this is the case. And of course, for finding out your fixing your your point of intersection, we need to know the x and y coordinate. We must know x distance and y distance. And for the case 1, since no S, x1 will be equal to B plus T cos of plus T plus A cos theta. Okay, like that you can find out. Okay, first triangle, then second triangle, and S is equal to 0, and y equal to simply same equation, changing the cos in place. Okay, S sine in place of cos. Okay, we are forming this equation. We will be able to fix this distance like that. And the coordinates of next P2 same way. Once x2 x1 you find out, then plus this distance. Okay, you can add it. Okay, this distance we can add it. This is how much. This is okay. This is your Q angle, and then Q angle. This is the what of B is there and A is there. That's all. Okay. Here in this case S may not be there. Suppose you want to, according to the sometime we may need S also. So this is the equation we are finding out. Okay. Like that, each and every point of intersection we are finding out the coordinates x1, x2, x3 and y1, y2, y3. In case of case 2, this first case, we are providing this S distance in place of here this triangle. We need to provide the S distance. We are adding it. That's all. Only we are adding S distance. And x we are finding out same way. We are finding out the y1, simply replacing the cos with the sine. Okay, simply like that we are continuously trigonometrically we are calling nothing okay difficult here. Same way we are doing. Once we know fixing, we are able to fix all the points, point of intersection, and okay, we will form the ladder track and we can lay the points on crossing. So okay, so and finally the all parallel lines will be connected. Okay, so this way this ladder track at limiting angles being calculated, designs are being designed, and the geometry of this thing is being fixed with the help of the diameters, dimension, the help of the dimension, the parameters what we have calculated. Okay, this is something about the ladder track at the limiting angle. Okay, this is whatever you have seen so far. This is about the designs of curved parallel tracks and as well as about the ladder tracks. Okay, this is something about it. So you can see some of the rules also. So whenever we form the new station yard and any modification in the layout of existing layouts of passenger lines, so we need to obtain the sanction of Commission of Railway Safety, and also any deviation from plans what are already approved plans are there approved by IRSE. If we want to deviate with it also, we must get a prior approval of Commission of Railway Safety. Okay, this is something about you must know. And also you have to little okay, some rules also you are supposed to know what it is stipulated in Indian Environmental Manual, para 410. Here, no change of super elevation over turnouts. Okay, and the points and crossing, that layout should not fall in a transition length. Okay, and there only there will change of super elevation, so that is to be avoided. But of course we can have in a curve. Okay, there the super elevation will be uniform. Okay, that's why there should not be any change of super elevation over turnouts. And there should be no change of cant. Okay, 20 meters, that means 20 meters outside the toe of switch and 20 meters beyond the nose of crossing. Okay, the points and crossing, this side 20 meters, that side 20 approach. You should not have any change of supervision. It's what it says. Okay, in example case, where no other way it is permitted. Okay, for the chief track engineer approval is to be obtained, but in this case that portion alone we have to keep the uniform supervision. Even though it is falling within the transit portion, that portion where the points are crossing lying both sides 20 meters, that portion we have to keep no change of supervision, should be uniform. Okay, that too with the approval of chief track engineer. Okay, is something about the rule. And coming to we already discussed something about the contour fracture, similar fracture. So in contour similar fracture, how this is being laid in that case, what will be the resultant radius of the turnout. Okay, when you are laying any points on crossing on a curved track, when it takes off from the median curve, forming a contour fracture, when it takes off inside the median curve, okay, forming a similar fracture, and in case and what will be our the resultant radius. Okay, that we will see here. So here The last slide, we have seen it is a straight turnout. This is your main line, this is your turnout line. Here the curvature is no, but here are designed curvature. Suppose in case of 1 in 12, it is 440 something will be there. In case of 1 in 8.5, some 600 something will be there. Will be your turnout radius. But when it is laid on a curve, for example, let us take it is a 1 in 12 radius. Points and crossing. 1 in 12 radius means 440 means that is 4 degree curvature. Okay, 4 degree already the turnout radius of curvature will be 4 degree. Okay, in terms of degree. But the main line main line is okay, in a curve the radius of curve is or degree of the curve is 2 degree. So what will be the resultant radius here? Okay, when it is straight, the main line will not have any curvature. But when we are bending, because our main line has to form the follow the curvature of the main line track. So when the straight track is being made as a curve, forming the following the main line track curvature, automatically the turnout also will be shifted inside. Okay, that means originally, when the points and crossing laid as straight, the turnout radius, turnout degree of the curvature is 4 degree. When it is laid on a 2 degree main line curve, what will happen? That curvature will be added. That means 4 degree will become 6 degree. That means 2 degree main line curve. When you are fluxing inside, automatically that will be added to the turnout radius. Okay, that means the degree will become 4 plus 2. Okay, the radius will become sharper. Okay, it will become sharper, and degree will become from 4 degree to 6 degree. Okay, that is in this case, that is a similar flexure. That's what the degree resultant will be equal to degree of straight turnout plus degree of the main line curve. Okay, in terms of radius, we want to write that RR equal to RM into RS divided by Rm plus Rs. Okay, this way we would write. That's nothing but simply we are substituting a relation between the degree and the radius of the curve. Okay, what is degree? Degree equal to 70 divided by R. If you are substituting it, automatically you will be able to get this relation. Okay, this is something about the similar flexure. Similarly, in the case of contra flexure, when it is a straight turnout, okay, the radius will be, the degree will be, suppose 1 into, let us assume it is 4 degree. But when the straight line of turnout is following the main curvature, when bending this way, automatically this curvature will be, okay, the turnout will be pulled this way so that it will become flatter. That means what will happen here? The degree of main line is 2 degree. When degree of the turnout is 4 degree, the resultant degree will be 4 minus 2 degree. Okay, that's why here dr equal to ds straight turnout degree minus degree of the main line. So dr resultant, dr equal to degree resultant. So degree resultant equal to degree s minus degree main line. So in terms of radius, we want to write rr equal to rm into rs, rm minus rs. Okay, this is the relation. Okay, you will get this is something about the resultant radius, resultant degree of the turnout radius when the points and crossing is laid on a curve. Okay, either the contra flexure or in the form of similar flexure. Okay, of course, in the case of symmetrical split, equal diversion take place. That means here the main line, since it is symmetrically split, here that rs equal to rm. Okay, that's what symmetrical design on normally we are providing, and for snag data and 1 in end of points and cross we are using. There the equal diversion will take place. Okay, so accordingly the crossing angle will become off, and thereby the radius also will become double resultant radius of the turnout. Both sides will be equal. Okay, this is something about the symmetrical split. Of course, this and all already we have seen. Anyway, for recollection, if you want to lay points and crossing on a this one passenger running line, you must use only 1 in 12 and flatter. You should not go for the 1 in 12. Okay, This is as per the manual provision 402. But exceptional case, in case of contraflexure, there we can permit 1 unit of curved switches, because when you are providing one curved switch in contraflexure, this will become flatter, okay, because of the effect of the main curve. So since okay, that we can follow. But in the emergency crossover, we can lay only in points of crossing, but only we have to ensure the movement of traffic only in the trailing direction. Okay, that we have to ensure. Of course, 1 unit of numerical we can use, but for stacked intent, because when you are using 1 unit of turnout as symmetrical split, it will give the advantage of 1 unit. That is why no problem. That is why it is permitted. Okay. And another advantage, many advantages are here as discussed earlier. And in case of when we are laying 1 unit of in the form of symmetrical splits. Okay, this is something about it. And as I already told you, when takes off from a curve, here when straight turnout, when you are providing in on a curve as a contraflexure, the turnout will become further flatter only. So here they have given some restriction, 1 in 12 or flatter only we have to provide. The resultant radius of it curve at any cost, it should not be less than 350. Like that we have to ensure. That means when you are laying 1 unit of, it is only 230 meter radius, but when you are laying in a contraflexure, it will become flatter. Okay, at this case, at any cost, it should not be sharper than less than 290. Not okay. When you are providing 1 unit of points and crossing on a curve, and the resultant radius you must get minimum 290 meter. It should not be less than 290 meter. So in this case, we can lay the 1 unit of points and crossing on a passenger line in a contraflexure form, but should not be sharper than 290. But we should take approval of principal chief engineer. It is in case of only space constraints normally. So otherwise preferable we should go for only 1 in 12 or flatter only. Okay, this is something about your contraflexure. And coming to 1 in 8.5 years similar flexure, that means when turnout takes off inside of the curve, we should not use 1 in 8.5 points and crossing, because what happens, so already 1 in 8.5 is very sharper, because 230 radius will be there too. Okay, but when you are providing as in a form of similar flexure, what will happen, the main curve also will be added here. That means the degree will become more, and the curvature will become sharper also. Okay, radius of curvature will become sharper. That means suppose 8 degree turnout, that is normally in the case of straight turnout. When 2 degree main curve is there, the resultant degree of turnout will be 8 plus 2, 10 degree will come. Okay, so that is why normally it should not be provided 1 unit of turnout. We should not be provided in a similar flexure. But 1 in 12 with the resultant radius, 1 in 12 we can provide. Even 1 in 12 we are providing, and we should ensure that the resultant radius should not be sharper than 350. Okay, should not be sharpened, because of the effect of the main end, it will become sharper, and we should ensure that the resultant radius should not be sharper than 350 meter. But of course we can go up to 290 meter, but 290 meter means we have to take approval of principal chief engineer. This is something about that whenever we are designing our layout. Okay, and in case of curvature, when the points and crossing are laid on a curve. Okay, this is something about it. And in case of turning curve also, you must ensure that any cost, this the radius of this one, turnout curve, this turnout curve. Actually, turning curve means what? After the crossing, the line, okay, turning inside of the main line towards the main line and running parallel to this one. That's called turning curve. And then generally this should not be sharper than 350 meter. Okay, that is that. Preferably, whatever, suppose 1 in 12 radius we are providing, same radius of curvature we can provide a turning curve. But if at all due to various reasons, space constraints and all, that is a case we can go up to 350. But even 220 also we can go. But in this case, we must ensure our complete track structure. The track structure should be at par to the main line. So standard, that means same PSC slipper we must use, same spacing and ballast profile, everything should be at par to the main line. In this case, you can go up to 220 meter. But preferably 1 in 12 turnout means passenger running line, same radius we can have. Okay, for smooth negotiation, or 350 of course. For 220 is only in the exceptional case, okay, if the space constraint is there. But that time you have to ensure the proper track structure, okay, standards you have to follow that, okay. This is something about it. Then coming to the isolation, the station yard, station we need some isolation, because for purpose of safety, suppose in case of main line movement is there, so whatever vehicle stable in the turnout, loop lines by mistake should not enter to the main line and get infringed, okay, resulting major consequences. So for avoiding that, what we are doing, and we used to do some isolation in the loop line. That means pretty well, and we are providing isolation and by providing a snack return. Normally at the each loop line, in case of double line, normally for the directional movement we used to provide the isolation. In the case of single line, and both sides of loop line will be providing the isolations by providing a 1 end of symmetrical split and connected to snack return or sand dump, okay. So that we are providing it, okay, so that when the main line is set for the movement of some traffic, that is symmetric, that isolation point, that will be set for the sand dump. The escaped vehicle, instead of going to the main line and infringing, it will go to the sand dump and derail, okay. So avoiding the major mishap, okay. That is something about the isolation, okay. But here you see important, it is this isolation we have, this is your main line, this is your loop line. Normally, we are providing snack in the form of snack, and we are providing it, and the sand dump, nowadays sand dump we are providing it. Here snack means 120 meter long, snack means this is 78 meter long, we are providing it at the end of the loop line. Purpose of isolation. Derailing switch, of course, we are using in some yards and all non-running lines, and shunting neck also we are using in passenger yards, and that purpose will be acting as a isolation as well as shunting neck, okay. So for the purpose of doing any shunting, okay, of vehicle. So but it is all signal control will be there. The moment is there, automatically this will be signal control. This is something about the isolations what we are supposed to have, okay. Keep in mind when we are designing our layout, okay. And powers of continuation of gradient steeper than specified, okay. Normally, whenever we are designing our stations and all, we must ensure that the gradient should be, okay, normally 1 in 1200. Recommended grade is 1 in 1200, but maximum steepest grade permit is 1 in 400, that we can do with the approval of GM, okay. Suppose in another way, otherwise normally we used to shift the station where we have the grade. Suppose it is not possible, then so we have to ensure that the normally flatter gradient, and maximum steepest gradient is 1 in 400. That is the case, we have to take approval from GM, general manager, and steeper than 1 in 400, that is the case, and up to 1 in 260, and we will take approval from CRS. With so many conditions will be there, and all those conditions should be fulfilled, okay. Really proposing, and we have to take approval of CRS for that. But steeper than 260, okay. In this case, see, this has to be submitted to railway board, and we have to take approval. That will be accorded of the through Chief Commissioner of Railway Safety, okay. This is not only example case due to various site conditions, okay, constraints, okay. Normally, preferably, we must ensure the grade in a station yard, it should be 1 in 1200. If at all it is 1 in 400 only, okay. This is something about the continuation, okay, of gradient, okay. Another, traps, slip sliding and catch sliding, and normally, as already discussed, it is intended to isolate except when it is not necessary that they should be open for the purpose of isolation, okay. So normally, for safety purpose, we used to provide some isolations, okay, for disconnection, okay. Any escaped vehicle, unnecessarily should not go into the running line, okay, and without any authority proceed. That is okay. Without authority proceed, no vehicle should enter into the some block section, okay, or main line, and should not infringe. Otherwise, it will result to mishap. That is why, and we are various locations, we are trying to provide some isolations. Now this one is slip siding, another one is catch sidings. Okay, so normally see, whenever any suppose this side is gradient, this is your station, and after that this is your steep gradient we have. What will happen when there is steep gradient? Sometime what will happen? Sometime there may be some potting a vehicle may take place. Once a potted vehicle, what will, because of the gradient, it will roll back. Okay, once it roll back, it is going, but it may enter without any authority to proceed. Okay, because it is unmanned, it just rolling back when it is coming. So it should not enter without the knowledge of station master, without the authority. It should not enter to the station premises. Okay, station limit. So that is why whenever it will be, the isolation will be there, that will be set to catch siding. Okay. Once this is when the train movement is there, it will be set to catch siding when towards this direction. So in this, any potted vehicle comes, instead of going into the station limit, it will be received, caught by the catch siding. Okay, catch siding. So that the any stabled vehicle will here. Okay. And this rolled vehicle, escaped vehicle should not go into hit with that and result in an accident. That is why this case we are providing catch siding. Okay, and another siding we have slip siding. That means any vehicle stabled in the yard also should not by mistake enter, escape into the block section. Okay, so already maybe train approaching will be there. Okay, any without the authority should not enter to the block section. That is why it may be because of the steep gradient. Okay. For example, this is your station yard, and after that sometime you may have some some gradients, steeper gradient will be there, some and steeper gradient will be there. If that is the case, what will happen? Sometime a mistake vehicle, it may go into the block section. For avoiding that, we are providing a slip siding, so that instead of going and infringe with the block section, it will be the slipped vehicle, escaped vehicle will be received in the slip siding. Okay, so that the major mishap can be avoided. So because of that, we need catch siding, slip siding according to the gradient existing in the approach of the station. Okay, here this is here. If the gradient is steeper than 1 in 80, from the 50 meter. Within the 50 meter beyond the this one topmost point, we need to provide catch siding. Here the other side, when the gradient is steeper than falling 1 in 100 and within the 50 meter from the outermost point, then we need to provide slip siding. Okay, this is something about the catch siding, slip siding. Okay. Okay, with that we'll conclude this video. Okay, this is my website. You can go into my website and see various okay. So various applications are also there. Earthwork calculations are there, longitudinal tracks, surfacing, real-time ducko, setting of ducko, RCC design and layout railways, whatever now we do. But here it is not available for curved track. For the rest of the connections, there are applications and you can make use of the applications. And here also some video and quiz also is there. That is for related to some railway topics, long rail track, points and crossing and curves. Okay, various topics are there. Okay, each topic. Okay, some videos are available. Whatever I am discussing now, I am just putting here. You can and go through. It will be in detail. And each and every topic, all three topics I am having right now. The quiz program also is there. You can put start and so you can practice the quiz. For questions are available. You can practice. You can update your knowledge. This is something about my applications. Okay. Okay, this is my mobile number. Also, you can contact me for anything, and this is my email address. You can leave some message. If you give your feedback, also any improvement required on this also can be sent to me. This is my mail address. Okay. Okay. So this conclude. Thank you for watching. We will meet in the next video.